You're welcome to Maths 101. We're now at the very last topic, matrices. Okay, so these are the topics we'll be considering: matrices and operations, determinants, and inverse of matrices. We begin with definitions and basic identities that you would need in the course of the topic, and later you will consider some examples. Now, a matrix is any rectangular or square array of elements arranged in a definite number of rows and columns. So basically it has to do with rows and columns. It's an array. Okay. A vector is a special case of a matrix which has only one row or one column. Okay. Don't worry, we will say the picture representative of it, but this is the definition of it for now. And then the dimension of a matrix is determined by the number of rows and its columns. Thus, a matrix with m rows and n columns is called an m by n matrix. M rows and m columns. Now, whenever the number of rows equals the number of columns, as m equals to n, the matrix is said to be a square matrix, or with dimension n, or depending on m, whichever dimension you're picking. Okay, so what does it look like? Now we know a matrix is a rectangular or square array of elements arranged in definite number of rows and columns. It looks something like this. In this case, we have rows, 1, 2 rows. We have columns, 1, 2 columns, with entries A11, A12, A21, and A22. In the example for a vector, we said it is only one with a special case with one row. So a good example of a row vector, a column vector, because now we're using a vertical one, is this one, A and B. So this is an example of a column vector because it's just straight down, vertical. Okay, but an example of a row vector will be this one, 1 and 2. You can see that the entries are in vertical location. Okay, so that's a row. Okay, let's look at the next example. So the first example, which we labeled A, capital letter A, is an example of a 2 by 2 matrix, in the sense that the number of rows and column is 2 and 2. So we say it's a 2 by 2 matrix, and because m equal to n in our case here, which is a square matrix. Okay, another example is this one you see here, this 3 by 3 matrix. How do I know it is 3? I have 3 rows, 1, 2, 3. I have 3 columns, 1, 2, and 3. So this is a 3 by 3 matrix. Okay, with these definitions in place, the next definition you need to know is what we call identity matrix. An identity matrix is a matrix in which all the elements on the principal diagonals are 1s, while every other element are 0. A good example is this 2 by 2 matrix. You can see that the diagonal entries, this one's here, 1 and 1, while the others are 0. For a 3 by 3, you have something like this. You get 1 in the first entry. Every other thing along the row will be 0. The first entry will be 0. The one in the middle will be 1, because the diagonals, principal diagonal is what we're looking at. And this last entry for the second row will be 0. And for the third row, you have 0, 0, and 1. You can see that diagonal entries are all 1, while every other thing is 0. So this is what we call an identity matrix. Okay. The next definition you need to know is what we call equality of matrices. Now we have 2 matrices are equal if and only if they have the same dimensions and the corresponding elements are equal. they have the same dimensions. You know what dimension is? The number of rows and columns are the same, and the entries are the same, they're equal. So look at this. We are given two matrices. This is a 2 by 2 matrix and another 2 by 2 matrix here. Because they both have the same dimensions, so 2 by 2, they are said to be equal on the grounds that we have that the A is equal to the X, the B entry will be the same as the Y entry, the C entry will be the same as the Z entry, the D entry will be the same as the D entry will be the same as the W entry, as you can see here. So the dimensions equal and their corresponding entries, elements are equal. Then they are said to be equal matrices. The next definition is what we call matrix addition and subtraction. Well, this will fall under identities because we want to see how to add and subtract two or more matrices. Now, if you happen to have two matrices, this matrix, this 2 by 2 and a 2 by 2, it could be a 3 by 3. Main idea is this. Whenever you have them, the entries, the number of rows and columns are always usually the same, so it's easy to add. So you can add the entries A with the entry X, the same location, okay? Entry B will be added to Y. Entry B cannot be added to W because it's not at the same corresponding entry location, okay? So W will be added to D, or D be added to W, and C will be added to Z. So you don't add a different location to the other, okay? So that's the rule. If you want to subtract, you do exactly the same thing, okay? So for a 3 by 3, it means you would have entries. Let me see how we can put a 3 by 3. So for a 3 by 3, you happen to have, say, 1, 2, 4, 0, 1, 9, 1 minus 1, 2. And you want to add it to another matrix, or subtract it to another matrix, 0, 1, 0, 0, 2, 1, 1, 0, 1. All you just do is add 1 plus 0, which is the location the same, 2 plus 1, okay, and 4 plus 0. You keep adding them to get your 3 by 3. So the first entry on my first row will be 1 plus 0, which is 1, 2 plus 1, which is 3, 4 plus 0 is 4, okay. For the next entry, 0, 0 plus 0 is 0, 1 plus 2 is going to give me 3, 9 plus 1 is 10, and 1 plus 1, now the third side, 1 plus 1 is 2, minus 1 plus 0 is going to give me minus 1, and 2 plus 1 is 3. And so that's your final answer for the addition of the two 3 by 3 matrix. Okay, so we'll do more examples, but the one here I've shown for you a 3 by 3. You'll see that of a simpler case later in the examples as we go along. Okay, so that's how to add. And if you know how to subtract, it's the same thing. Just wherever you see addition, you subtract. Okay, the next definition you need to know is what we call a zero matrix. What's a zero matrix? A matrix whose elements are all zeros. So all the entries are zeros is called a zero matrix. The zero matrix can be different dimensions. So you could have the one of 0, 0. What is the special name for this kind of matrix? Remember, we said it's called a vector. A vector. They're special cases. In this case, it is a zero matrix. Okay. The next thing we're going to know is how to multiply. If you happen to have two or more, or even a scalar multiplication, what do you do? So in the first example, or the first instance of identity you need to know is this, what we call the scalar multiplication. You want to multiply a scalar by matrix A. So we have the matrix, this is a matrix A, and our scalar K is multiplying it. What do? You simply just carry K and multiply each entry, each of the elements one after the other by K, as you can see here and here. That's how you multiply a scalar. So if I happen to have 4 outside my matrix, say 1, 0, 0, 1. Remember what this is. This is a unit matrix, and also identity matrix or unit matrix. What would be your answer? You just simply say 4 times 1, which is 4. 4 times 0 is 0. 4 times 0 again, 0. 4 times 1 again, and that is 4, which is your answer for your matrix. Okay, that's the answer. So that's how to multiply for a scalar multiplication, multiplying it to a matrix. Now, what if you have two matrices? You want to multiply two matrices. So there are rules for multiplying two matrices. Okay, the rule says here, two matrices. Sorry, let me get that sorted. Two matrices can be multiplied if and only if the number of columns of the first matrix is equal to the number of rows of the second matrix, or vice versa, the number of rows equal to the number of columns. Okay, look at this. This is a rule, isn't it? The number is just 1, 2, and the number of columns is just 1. So sorry, one row, one row and one column. So you have that, which is equal. So which makes it possible to multiply. And this is how you go about the multiplication. You do a times x plus b times y, which is what you have here. Okay, look at this now. Number of rows, number of columns. Can you see? So it's possible because I can take the number of number of columns times number of rows. Okay, number of columns 1, 2, number of rows 1, 2, which is exactly what we had stated earlier. So I can multiply easily. So if I want to multiply now, same thing you saw me do for the number of columns times the number of rows here, number of columns times the number of rows. Okay, you can see that we have 1, 2 columns, rows 1, 2. Okay, so that made it possible to do that. So now we want to multiply this. What do you think happens? In the same way we multiply this, you take this first one and it goes down, which is what you saw here the first time, which is the entry here. And then you take the second one and then you go down again, which you can see here. Basically c times x plus d times y. Okay, so that's how you multiply the one with 2 by 2 multiplying one column. Okay, what if it's a 2 by 2 times another 2 by 2? How would that look like? So for a 2 by 2 times a 2 by 2, you do what we did before. You take it and multiply this. You take the second one and multiply this, which gives us this first part of the entry. To get the second part, you take the first one again. You take the first and multiply this. You take the second, which is what you can see, the upper part here, and you multiply. And then you take the second one and multiply this again, which you see down here. So that's simply the rule of multiplying for matrices. For a 3 by 3 in a similar way, So basically you're saying you're going to be having A, B, C times x, y, and z. So what do you think you get? Definitely this would be something like ax plus by plus cz. So if I happen to have, say, d, e, f down here, same thing. When you were multiplying this, you then do the same. You first do this and get the one for up, then you do this and get the one for the one next to it, which is going to be like dx plus zy plus fz. Okay, so that's what you're going to get, and then you can extend it for that for a 3 by 3. Okay, so with that said, you can pause the video and study what the identity says. We're going to apply them shortly anyway. So let's continue. Now we say the possibility of multiplying is true, but when we have a and b that they are square, you understand what we mean by square matrix, meaning that the n equal to m, the number of rows and columns are the same dimension. Both a and b multiplying ab, a times b and b times a, b matrices a and matrices b, they are defined. That's it. You can have ab and you can have ba. But it's not always true. Not always true that this thing will be equal. It's not always true. So that's what we're saying here. That it's not always true that they are equal. Because square multiplication matrices, they're not commutative, okay? They're not commutative in matrices, okay? It's not always the case, okay? So, but it exists, but not necessarily that they are commutative. Okay, so let's go to the next identity you need to know, and the next identity you ought to know is what we call the determinant of a matrix. So for a 2 by 2, to get the determinant of a 2 by 2, which is the founding main rule, once you can get the determinant of a 2 by 2, you can extend it to find the determinant of a 3 by 3, but there are secret rules in applying them. Okay, usually for starters and at your level, we want to focus more on the 2 by 2. So to find the determinant of a 2 by 2, so a determinant is actually a single value you get. I haven't taken the determinant through some mathematical processes. Okay, so the determinant for a 2 by 2, so you have a matrix A labeled in this form. You can see that the label is slightly different. On the column, first column you have A1, A2, and the second column you have B1, B2. Okay, so if you're looking for the determinant, another way of writing determinant, this long thing I've written here, you just write it as det A, because we're considering determinant A, the matrix A. And in symbolic form, it looks like this. Okay, so you're told to find the determinant. All you simply do is take the entries, these entries, and put them here, but not a curve now around them, but a straight bracket, as you can see there. Okay, the straight bracket hand is there. So that makes you know you're finding the determinant. Okay, so the rule is that if you're looking for the determinant for a 2 by 2, you simply multiply diagonally. You simply multiply diagonally this way. That's A1 times B2, and subtract the multiplication this way. Okay, did you get that? You multiply this way first, and then subtract the multiplication this way. Okay, but that's one for finding the determinant of a 2 by 2. Now to find the determinant of a 3 by 3, which is the 3 by 3 matrix on the screen here, you want to find this determinant. The thing is, you will need the knowledge of a 2 by 2 to find it. Okay, so which is what we know already here, but there are some things you will need to know first. So let's read through what you see on the screen. Okay, now to determine the determinant, this is obtained by striking out the out row and the seed column. Don't worry, I'll explain that to you, containing any element, and then compute the determinant of a 2 by 2, like I was saying. This determinant is called the minor of the corresponding element. For instance, so let's explain what we're saying. So now we want to find the determinant of this. First, we consider the location. So we look at this upper row. That's the key one we'll be looking when finding determinant. Okay. Now, along this location for a 3 by 3, this location is called location 1, 1, because usually you label A1, 1. Okay. A1 is located there. So what we'll do, let me see how I can make my pen a little bigger. Let's see, because I need to hide some things first. Let's make the stroke wider. Okay, that should do. So what you do is, where A1 is, we want to find the minor of A1. This is A1. You cover all the entries along A1, so you don't see anything there. Can you see? I've covered everything here. So your 2 by 2 matrix is this entry you can see, this one that is left on the board on the screen, which is what I have written here. Sorry. So you now have it. This is the minor. The minor of A1 is what you see here. So you just simply multiply, just like we did when we were finding the one for a 2 by 2 up here. You take the B, make it tinier now. So you take the B2 and multiply C3, which is what you can see here, and then you subtract the B3 times C2. Okay, so that's how you get the minor at the point A1, the first entry. Okay, so I'm coming. We still have some steps. There are 3 of them. Like I said, you consider, basically you're considering the entry along the row up here. Okay, so you take A1, it will now take the determinant at this determinant, and then you subtract B1. You take the determinant of B1. So how do you get the 1 at B1? So let me make my pen broader again so that you can see how to do that. Don't worry, you would practice and get it in time. Okay, so at B1 now, everything along B1, I just cover them. You don't see anything there. Okay, So what are you left with? You're now left with A2, C2, A3, and C3. So you take the determinant of this just like we did before, and plus the third entry. What's our third entry? Our third entry along the column, like I said earlier, is C1. Okay, and at C1, what do we have left? If we cover the entry C1, everything along C1, just cover everything. What are you left with? You're left with A2, B2, A3, B3. So if you ask for the minor of A1, you're simply finding the entries when you cover all of A. Okay, minor at let's say B2. If you're told to find the minor at B2, what do you do for B2? Just exactly what I did before. I won't make my pen a little brother. So you want to find the minor at B2. What you do is this. Along B2, you cover everything along B2. You cover everything both vertically and horizontally. What are you left with? You're left with, so what you're left with for B2, sorry, I'm coming. So you want to find the minor of B2. That's what I'm trying to get there for you. So to get it, it simply means that the determinant, the minor is going to be A1, C1, A3, and C3. That's what you see on the screen, don't you? These entries and all this box. This one, and this one. Okay, so that's how I got that. So that's how to find minors. Okay. Sorry, I need to clean, not write everything. Okay, so let's retreat again. I'll take it again. Make my pen thinner now. Okay, so to find the determinant again, this determinant is called the minor of the corresponding entry. So for instance, for A1, which is what you saw me do, just simply cover what entries are at A1, and what you left right here is the determinant, or along A1, the minor. Okay. Now again, like I said earlier on, a determinant is a single number associated with a square matrix. So you must have a square matrix to be able to get a determinant. Okay, let's move forward because we're still building on finding determinant of a 3 by 3. Okay, so we will need an algebraic sign because all of these entries for a 3 by 3, each one of them has a sign where they are seated. Each book I'm writing, each location has a sign. Now, in order that you don't start cramming the sign, there's a formula, and that formula is called the sign factor. So an algebraic sign is assigned to each minor, and it's called the sign factor. What is the formula for the sign factor? This is the formula. Minus I raised to the power I plus j. How did they get this I? What is I? What is j? How did they get it? Simply compare the entries. Like I was saying earlier, that each location has a number. Okay, so the rows along the side, you can see where A1, 1, A1, 2, A1, 3. So the I here is going to, for A1, at A1, 1, I will be 1, j is 1. At A1, 2, I will be 1, j will be 2. At A1, 3, I will be 1, j will be 3. So whenever you're given a matrix, just compare the matrix you're given with the standard way or notation of writing the matrix to know your I and your j. That's all you need to do. Now, for instance, now we want to find the sign factor for A1, the location at A1. Now you know A1, if I compare A1 with this standard way of writing it, it means A1 is actually supposed to be written as A11, meaning that my I is 1 and my j is 1. So if I substitute it in the factor formula, this is our factor formula. This minus 1 raised to the power I plus j. Remember that I is 1 and j is 1. That's how I got minus 1 raised to the power 1 plus 1. And minus 1 raised to the power 2, that's when you see 1 plus 1, it is 2. It's simply 2. So minus 1 raised to the power 2 is going to give us a positive sign, because minus 1 times minus 1, because minus 1 times minus 1 is going to be 1 minus times minus plus 1 times 1, 1. So you have a positive sign in that location. That's the sign factor for A1. Okay, so the next thing is the cofactor of any element will be denoted by the corresponding capital letter. For instance, for the cofactor of A1, this small letter A1, its cofactor is labeled a capital A1. Meaning, whenever I ask you to find the cofactor of A1, I simply want you to find this formula, this thing here. How did I get that? You find A1 on your formula, on your matrix, okay? You cover all the sides and get its matrix, which is what you see here. And whatever you get, multiplied by the sign factor of that location, which is here. And what is the cofactor symbol for A1? For small letter A1, it is capital letter A1. So when you solve it, you will get what you see here. I'll take that again. Whenever I ask you, or anyone asks you, to find the cofactor of a particular element in a matrix, whatever matrix we give you. In this case, ours was A1. What they want you to find is capital A1 equal to the sign factor along A1, which is minus 1, or raised to power 1 plus 1, because at the location of small letter A1 is the same location with this, times the matrix, the determinant of the minor of A1, which is this one, which is B2, C2, B3, C3. You can multiply this out and get your final value, which is what you can see on the screen there. Supposing I tell you to find the minor, to find the cofactor, of C3. I want you to find the cofactor of C3, meaning that you look at our 3 by 3 matrix, because that's what I want you to look at. I've given you the matrix. C3 is here. You first need to find, so remember the way it is, we're told that it's a capital letter. For instance, the cofactor of A1 is a small letter A1. So we're looking for that of C3. It means that C3 will be capital letter C3. And this will be equal to the sign factor minus 1. What will be our I for C3? C3 is at 3, 3, which means that my I is 3, my J is 3. And my determinant, because that's what we said we will do after getting that for A1. My determinant, now I cover all of this. I cover all of here to get the minor, which would be A1, B1, because that's what is left up on the screen here. A1, B1, A2, and B2. So you multiply everything. I can see here that I'll have 3 plus 3, which is 6, minus 1 raised by 6, because the power is even, definitely is going to be a positive sign. Okay, and then you do multiply this way, which is A1, B2, minus multiply this way, minus A2, B1, which is your final answer. Okay, so as we continue, we'll do some examples that will involve numbers for entries, and you'll see how we apply that. Okay, so let's continue with what we're doing. So I've stated here that you can do the same for cofactors of B1, which means you can check for capital B1 if you're to find cofactors, and so for C1. And finally, that thing which I was trying to make us see, that if you're given a 3 by 3 matrix and you're told to find the determinant, the formula is also there, but you needed to know how to find cofactors, you needed to know how to find minors first. And now that you know how to find the minors and the cofactors, the formula for the determinant of a 3 by 3 is what you have here, this formula here. So for a 3 by 3, you simply take the determinant, which is going to be A1, the entry, this A1, plus capital A1 plus B1 times B1 plus C1 times C1. So that's the formula for the determinant of V3 by 3. Let's continue now. The next thing you need to know is what we call the transpose of a matrix. What do we mean by transpose? All it simply means, which is what we have written here, when they say find A transpose or B transpose, you're just simply saying A with a capital T on top of it. But what does it mean? It means simply you should write your rows as columns. Every row will be written as column. So basically, you're copying this and pasting this way. You see that? Then you copy this and paste this way. So that's just A transpose. So your A is given as this. Your A transpose is copy the A and write it as a row. Copy the B's, which are columns, and write them as rows. And that is your A transpose. What if the matrix is a 3 by 3? You got capital letter B. The total transpose, find the B transpose. Again, you write your column as a row. You write your column B as a row. You write your column C as a row. So you just copy all of this, paste it this way. Okay, that's just basically it's as simple as that. Okay, you can picture yourself copying, or maybe a sticker. You just pick it, all of it, and just pick it and arrange it this way. You pick this one and arrange it this way. Pick this one and arrange it this way. That's all. That's what they mean by a transpose. Okay. Now we had seen earlier how to find cofactor of entries or elements of a matrix. The next one is what we call the cofactor of a matrix itself. The cofactor of A, written in short form cof A, as though you're coughing, is a matrix obtained by replacing elements of A, Ij, of A by their corresponding cofactors. Remember how to get cofactors. Cofactors are capital letter A1, capital letter A2, if you remember. And for the 3 by 3, then we had B1, B2, B3, C1, C2, C3. If you can find each of this and write them as a matrix, then you have found cof A. That's what it's saying. Okay, you can see your lecture notes for details on how to find and examples, more examples on this. Okay, the next thing you need to know is what we call adjoint of a matrix. Now you know what the cofactor of a matrix is writing all the entries, the single entries, replacing them with their cofactors. So this will not be B1, this will be C1, this will be A2, capital A2. So once you are able to write or find all their values, then you have found the cofactor of the matrix itself. Now back to adjoint of a matrix. The adjoint of a matrix A, written as this, Adj A, is the transpose of the cofactors of the matrix, or the transpose of the cofactor of the matrix cof A, and adjoint is simply written as this. So after finding, if you want to find adjoint of A now, all you need to do is find all the cofactors. That's that matrix. When you found A1, you found A2, you found A3, you found B1, capital B1, capital B2, capital B3, capital C1 now, capital C2, capital C3. That will give us our cof A. Is that not so? So if you want to find adjoint, you simply take the transpose of what you have there. That's why they said cof transpose. So if I want to find the adjoint of this A now, adjoint of A, I simply would write this as a transpose. Remember what I said? I'll write all of this now as a row, which means I'll have A1, B1, C1, and then I'll write this one too as a row. That means I have A2, B2, C2. I also write this as a row, which is A3, A3, B3, and C3, which is your final answer. So if you found values, numbers, you just replace them. So that's what adjoint of A is. So in formula form, if if you're told to give us the cof of a matrix, all you just do is tell us that we're picking all the cofactors of the elements of a given matrix, while the adjoint of the matrix A, the noted adjoint, is this formula of A transpose. More to know. The next thing you need to know is what we call the inverse of a matrix. It's denoted A inverse. Note carefully, this A inverse is not the same thing as 1 over A. It's just simply a definition, okay? We just need you to know that, okay? So, having said that, to find the inverse of a 2 by 2 matrix, you use this formula here. If you're given a 2 by 2 matrix, so you need to know this by heart. So you know how to find the determinant of a 2 by 2. We had seen that earlier. And to find the inverse, you just simply take 1 over the determinant of the 2 by 2 matrix, and then the entries of the 2 by 2 is rearranged this way. You just multiply them and you have found the inverse. But in general, if you have any square matrix, to find the inverse, this is the formula for a general case. But for 2 by 2, you just simply use this, okay? But in general, for a square matrix and you're looking for the inverse, you just take adjoint of A and divide it by the determinant of A. Remember what adjoint of A is again? Adjoint of A is simply cof A transpose. Let me take us back to our screen where we were. So adjoint of A is cof A transpose. Okay, you can rewind the video, play back, and see what I've explained thus far. There's a very critical definition here that I know we always ask in most of our questions, and that is, what is a singular or non-singular matrix? Now, a square matrix, you know what a square matrix is by now too, because we also asked that. A square matrix is a matrix whose the number of rows and columns are equal, okay? So, a square matrix for which its determinant is non-zero, that is, whatever answer you get is not zero, is called a non-singular matrix. Else it is called a singular matrix. So if after finding my determinant of my matrix, I get it to be 1, so long as it's 1, it means that matrix is non-singular because it is non-zero. But if it turns out that it is 0, then we say it is what? Singular. Okay? Now, hence a square matrix has an inverse if and only if it is what? Non-singular. So always note that. We will continue now with examples. Okay, so for examples like I did earlier, I had explained to us how to add and subtract matrices, and we said that we just pick the entries one by one and join them together. So we're subtracting these two matrices that you can see on the screen. So the entries minus 1 and 2, they want to subtract, so we have 1 minus 2 there. Minus 3 is taken away 5, so that's minus 3 minus 5. 3 is taken away minus 1, so that's 3 minus 1, because there's a minus subtracting them, okay? And then another 3 minus 7, which is 3 minus 7 here, okay? So that's how we got the row, the next line you see on the screen there. So if you simplify further, what do you see? 1, I have 1 there and I'm owing 2. Definitely I'm still owing 1. I'm owing 3 and I'm owing 5. Definitely I'm owing 8 of them. Now, minus times minus here is plus, so 3 plus 1 is going to definitely give me 4. I have 3 naira, I'm owing 7 naira. Definitely I'm still owing 4. So that's how we got the entries of this final value here. Okay, simply by adding, subtracting these two matrices is what we're given. So once you see the bracket, don't be scared, they're just matrices. All you do is work with the respective entries. Now on the screen we have to multiply this matrix. And I had shown us earlier, we have studied this multiplication. I even showed us the one for that of a 3 by 3. So now we have an example to multiply here. We're told to multiply the 2 by 2 matrix times the column matrix or the vector. So this is a 2 by 2 matrix, and then we have a column matrix here. we can see that the number of rows and the number of columns, it tallies, so we can multiply them, can't we? Okay, so since we can multiply them, the rule is right here. I've copied it for you here as an image. We're using this, and you saw what we did. From this one, we just multiply down this way to get the first entry. So we did the first way down, and then we did second way down. Okay, same way we're going to do here. Okay, so don't forget the rule. So we're going this way and multiplying down this way. So that will be 2 times 3 plus minus 3 times minus 2. You can see it here. Same way, 1 times 3 plus 4 times minus 2. See it here. Okay, same way. So if you simplify further, simplifying this, 2 times 2 is 6. That's why you see my 6 here. There's a plus sign between the two of them, is that not so? Minus 3 times minus 2. Minus times minus is plus, and 3 times 2 is 6. So that's how I got the simplifying for this one, simplification of this one to be this. Okay, now we're at this lower one. 1 times 3 is 3. There's a plus sign between them, if you recall, by the standard rule here. That's the plus here. And 4 times minus 2 is going to give me minus 8. Okay, so that's how we got the values for this next step here. Okay, so we're still simplifying. 6 plus 6, 12. I have 3 naira and I'm owing 8 naira. How do I know I'm owing? Because plus times minus is still minus, so I'm owing 8 naira. Okay, so I have 3 naira, I'm owing 8 naira if I pay, and they're lately left with 5. I'm still owing 5. So that's how we got the final answer. There's nothing more to do. So that's our final answer. Okay, so that's how to multiply. You can check your lecture notes for more examples of multiplication and all of that. You'll see more examples and exercises. Okay. So now we have an example before us again. And this example, we're given a 3 by 3 matrix, a square matrix. You know what a square matrix is now because they have square matrix, meaning that they have equal number of rows, equal number of columns. Okay. And we're told to evaluate the cofactor of A to 3. So if you compare the two matrices, if you remember how to find A to 3, A to 3 would mean that's going to be, so we know this A11, A12, A13. This would be A21, A22, A23. So we found A23. It is at this point here. You just need to know the labeling. So let me claim that. We found where A23 is. So we're trying to find the factor at A23. Okay, we know. We just write it in capital letter forms and so. And we need to find, so the formula we use for that of A1 is what you see here, if you remember. So at A23, all I need to do is cover here. So I cover everything here. I cover, sorry, not there. Everything I have to do should be along A23. So I'm covering everything that is along A23, and then I'm covering everything here too. Wherever I know that A23 is just there. So what I'm left with is 1 minus 2 for my determinant, 5, and minus 4, which is what you see right here. You agree with me? Okay, so we need to find the sign formula too. The sign formula is minus, if you remember, the sign formula is minus 1 all raised to power I plus j. Okay, so that's what I'm doing here. And now we have minus 1, and our A is at the location 2, 3. So my I is 2, my J is 3. That's what you see on the screen there. So with that said, we just open our bracket. We know to multiply this way and subtract this way for determinant. Is that not so? Okay, so here, this first one, we have minus 1, or is about 2 plus 3, which is 5. That's why you see 5 in my numerator there. And if I multiply this way, I get 1 times minus 4, which is what you see there. The minus sign in between, because you know there's a minus sign in between this multiplication here too. So and then I'm doing multiplying this way, 5 times minus 2, which is what you see in this bracket here. Okay, so we're moving forward. So what do you have if you simplify? Now the power here is odd, so definitely my value would definitely be minus. So that's how I got a minus. Once it is even, it will always be plus. If the value on the after adding is odd, it's going to be negative. Okay, so because it's odd, so we have gotten a negative sign for our position sign, factor sign. Okay, so back into our bracket, this bracket here now. In this square bracket, 1 times minus 4 is definitely minus 4. There's a minus sign in between. Look at it here. So in this bracket, 5 times minus 2 is definitely minus 10. I've kept it in the bracket because there's a minus sign outside, so one has to be careful with our signs because it can really cause issues. You just leave it in the bracket. So I left in the bracket, and then I did minus times minus to give me plus. So that's how everything changed to this, which you see here. Because there's a minus in front of the 4, and it comes down, and the minus times minus has become plus, and there you have your 10. Okay, so now I'm owing 4 naira, and I have 10 naira in my bracket here, just this bracket here. Okay, so in that bracket, I owe 4 naira, and I have 10 naira. If I pay back, I'll be left with 6 naira. But there's a minus sign outside because that's a sign we got from factor sign, if you remember. And the final answer is just going to be minus 6. So that's how I got the value for the cofactor of the location A23. It's possible the question can be changed and you're told to find, to evaluate. So you can also try that. You can find the cofactor for maybe, let's say, minus 4. Since it's uniquely there, you can check for minus 4. So you need to find what is the lettering for what number, what is I, what is J for this location, and you solve as you can see on the screen. Okay, let's continue. The next question says that we should, using A as in the previous example, which is still what I've written here, is what our A is, that we should find A transpose. So what do we do with A transpose? We write all columns as row. You copy this and paste this way. You see that? Just 1, 4, 5. So 1, 4, 5. You copy this again. Copy all of this and paste this way. So 2 minus 2 minus 3 minus 4 minus 2 minus 3 minus 4. And finally you copy this and paste this way, which is 3 minus 1, 0. So that's all. That's your answer for A transpose. Very simple. And one of the easiest thing to do. Just remembering what you're doing, that's a key thing. Okay, so that is that for that example. The next example, example number 5, we're told to find the determinant of B and also to find B inverse. So how do we find the determinant of B? It's a 2 by 2 matrix. So for a 2 by 2 matrix, this is the formula. I'm using this. Okay, so for a 2 by 2 matrix, you just multiply this way and subtract this way. So we're multiplying this way and subtracting this way. So to multiply this way, we have 1 times 3, and then we subtract this way, which is 3 times minus 3. 1 times 3 is 3. My minus sign is out here. In the bracket here, I have a minus 9. That's how I got a minus 9. Minus times minus is plus. So I'm left with 3 plus 9. And our final answer is 12. So we found the determinant, which is 12. That's your final answer. If I went fast, you can pause the video and go through it slowly. Basically, don't forget this formula for a 2 by 2 and that of a 3 by 3 as I had shown us earlier. Again, you can refer to your lecture notes for more examples or exercises. Next, we're told to find B inverse. So how do you evaluate B inverse? If you recall, before now, towards the last definitions and basic knowledge you needed to know, we are saying that for a 2 by 2, the inverse is 1 over the determinant of A, the inverse of A, 1 over the determinant of A, and then you rearrange the entries of the determinant as you can see on the screen there. And that if it's any square matrix of choice, of any given square matrix, that A inverse is adjoint A over the determinant of A. Okay, so we're told to find B inverse, and this is our B. B is this. So again, we just simply compare. So we need to know this formula by heart. Though it is A inverse, we're looking for B inverse. So it means we're going to have 1 over determinant of B, which is what I have here, and then you rearrange the entries of B. So what's our A? Looking at this, A is 1, B is 1, B is minus 3, C is 3, and D is 3. So that's how I got all those values. So I just substituted back into this formula. Okay. So we had earlier on sought determinant of B. If you check, you can rewind the video, you see it was 12, which was because that was the I part of the question. We're not II. So if you see a determinant of B, we know it is 12. So that's why there's 12 down here. My D is 3. So I put 3. There's a minus sign in front of B there. So there's a minus open bracket minus 3 because my B has a minus sign, so I'm careful with the brackets. And then there's minus C, there's minus, and my C is 3, and finally my A, which is 1. So just substitute everything carefully, and then you simplify. So we're simplifying now. How do we simplify? You remember the scalar multiplication we did when there was K outside? So this is my K, it's 1 over, this is my K, is 1 over 12. So I just multiplied in this 1 over 12 times 3, 1 over 12 times 3 here, 1 over 12 times minus 3, 1 over 12 times 1. So 1 over 12 multiplies 3 will give me 3 over 12. 1 over 12 multiply 3 is 3 over 12, that's 3. 1 over 12 multiply minus 3 will give you minus 3 over 12. 1 over 12 times 1 is still going to give me 1 over 12, not minus, okay? So just multiplying them using my scalar multiplication. And then simplifying. How many times can 3 go here? It will go 1 time. 3 into 4 and 12 will go 4 times. That's how I go 1 over 4. Same here, same here, same here. Nothing happens with this entry because there's nothing to simplify. And that's how we got the value you see on the screen there. So that's our B inverse, our matrix B inverse. So like I said earlier, you can rewind, pause the videos wherever necessary, and you can refer to your lecture notes for more examples. Thank you.